guys, and welcome back to the PyTorch tutorial. This is going to be a continuation of the previous videos that I made about gradients. So before you watch this video, make sure that you watch the previous videos that I made about gradients theory, so that you can understand the basic theory behind gradients before we start the implementation of gradients using Jupyter Notebook. So the first thing that we're going to do is import torch, and we're going to create a variable x, and it's going to be a random number, and this tensor is going to have 3 elements. So we're going to print x and x.shape to see the output. As you can see, we have 3 elements in this tensor, and the size of this tensor is just 3. Last time we talked about how to enable gradient tracking and build a computation graph using PyTorch. So if you want to turn on gradient tracking for any variable, you just have to provide the requires grad attribute and assign it the value true. Here we notice that we didn't provide the requires grad parameter and assign it the value of true, so there is no gradient tracking for the previous variable. But for this one, since we have provided the parameter requires grad equal to true, when you print x again, you'll see that in the output there is going to be an additional requires grad equal to true, which confirms that gradient tracking has been turned on for this variable. But for the previous variable, we will not have this parameter added to the tensor function. Whenever we do this, PyTorch will create a computational graph and keeps track of the gradients. So any kind of operations that we perform on this variable x, it's going to be added to the computational graph because we have enabled gradient tracking. The next function is going to be y, and y is going to be an addition operation, and it's the summation between x and another number 2. Since we turned on gradient tracking for the variable x, this is going to be a computational graph, and y will be the sum of x and 2. First, we will do a forward pass to calculate y. Since requires grad is true, y will have an attribute called grad function, which will be assigned the function add backward for the addition operation. So when you create a function by using by performing some kind of computation on a variable in which gradient tracking has been turned on, that function is going to be assigned an attribute called grad function, which is assigned by PyTorch. And in this case, the grad function will be given the value add backward because the computation that we are performing is an addition operation. And add backward is going to keep track of the gradient dy by dx, because if we want to go backward and compute the gradients, we have to compute dy by dx. This is the only gradient that we have for this simple operation. This will calculate the gradients in the backward pass, but note that we haven't started the computation because we're just moving forward for the time being. And this is just the derivative of y with respect to x. Now let's print the function y and see what's happening. We haven't defined y here. We have to run this code first and then run this code next. Now you see that the original tensor was this one, and the gradient tracking has been turned on. After adding 2 on each of these numbers by using broadcasting, this is just another element-wise operations that we have discussed in the previous video. The new output y is going to be this. And notice that now, instead of having the requires grad equal to true parameter, we have the grad function, which is only assigned for functions in a computation graph, and it's given the name add backward 0. And whenever you have a function, it's going to keep track of the gradients for that specific function, and it's going to compute the gradients once we start going backwards. But for now, it's just saying that I'm keeping the gradients dy by dx in case we want to compute those gradients. Let's do another operation. Notice that we have moved from x to y. What if we want to add another function and add another variable z? Here, z is going to be y times 2. And finally, z is equals to z dot mean. Notice if we just use this, the output is going to be a vector. And if we perform a reduction operation, in a previous video about reduction operation, we mentioned that the purpose of a reduction operation is to reduce the number of elements of a tensor. And mean is one kind of reduction operation, and it's going to compute the mean of y times 2, this output, and then the output from the final mean function is going to be a scalar. Now let's see, first let's print the first notice here that we are just multiplying y by y and multiplying it again by 2, and we have this output. Now notice that since we added another function, now it's going to be mul backward, because z is a new function and it's a multiplication function. And we're adding another operation called mean, and this is a reduction operation. And if we print z again, notice that the mul backward has now changed into a mean backward, because we're computing another operation called mean, and the final output will not be a vector but just a scalar. Bear in mind that we have not started the computation of gradients. We are just moving forward in the computation graph. But since requires grad is enabled for x, the original variable, PyTorch keeps track of the computational graph from z back to y and back to x. Now we have finished reaching the final output, and it's a scalar. Now let's start moving backwards and start to compute the gradients. In order to do this, in the previous video when we discussed about the theory behind gradients, we have to use a backward function to start computing the gradients and start the process of backpropagation. So when you call z dot backward, we're gonna call this function on the final output. It's going to compute dz with dx. Since we have 3 functions in this case, we're gonna have to compute intermediate gradients, and then we're going to multiply them by using the chain rule and move back from z to x. So we have to compute dz by dx will be the final computed gradient. And if you want access to those gradients and you want to see the output, you can use the .grad attribute on the original variable, in which you have turned on the gradients. You can see what those gradients are. So x has an attribute called grad, where the gradients are stored. So when you print out the gradients, these are the final dz by dx, the gradients which have been computed for the entire computational graph, and you can access it by using the original variable in which the gradient tracking has been turned on. Notice in this case, for the final output, we only have a scalar. But what if we have a multi-dimensional output? One thing to note here is that when computing the gradients, PyTorch is doing a multiplication of a Jacobian matrix and a vector. Whenever you have a multi-dimensional output and it's not a scalar, PyTorch under the hood will use a Jacobian matrix multiplied by a vector and give you the final gradients as a vector, and it uses the chain rule for the product. And we have seen this in detail in the video when we talked about the theory about gradients. So make sure you watch that video in order to understand the detailed process. But here I'm just going to explain how to implement this for a multi-dimensional output. Since z is only one value, for the previous case, we don't need to pass an argument to the backward function to compute the gradients. Notice here, when we called the backward function, we didn't provide any kind of argument to this function because z is a scalar and it only has one value. And we don't need to provide any arguments to compute the final gradients. But if you have a multi-dimensional output, you're going to have to provide an argument for the backward function, otherwise it will give you an error. But if z is not a single value, we must pass a vector to the backward function, otherwise it will not work. Let's use another variable c without computing the mean. So instead of computing the mean, let's just use the multiplication function because the output of this function is still a vector and not a scalar. So we're going to remove the final operation, mean operation, the mean backward, and we're just going to store it in a new variable c, and it's going to create a new computational graph where the final output is going to be c. Now when you call the backward method on c and not on z, you're going to have c which is not a single value but rather a vector, because the output is similar to the previous z that we have computed before computing the mean. We can print to see what the final output is. Here we can see that it's a multiplication function and the output is a vector and not a scalar. And if you call the backward method on a vector output, it's not going to work. See that there is a runtime error, and here it says grad can be implicitly created only for scalar outputs. This means you can use the grad or the backward method only for scalar outputs without providing any arguments. So we're going to create another tensor, and it's going to have the same shape as the input, or the output in this case, and it's going to contain 3 elements. The reason that we are doing this is just providing this vector v, which is going to be multiplied with the Jacobian matrix to provide us the final gradients. And PyTorch requires the user to provide the vector which is going to be multiplied with the Jacobian matrix in order to give you the final gradient. So here we're just going to give some random values as elements for the vector, and then we're going to pass it as an argument to the backward method. And now when we call the backward function, we're not going to have an error because we have provided the vector, and x.grad is going to give us the final computed gradient, which is going to be dc with dx, because now we're using a new function called c. And notice here that it's not going to give us an error, and it's going to give us the final gradients, which are computed by using a multi-dimensional output. Next, we're going to see how to prevent PyTorch from tracking gradients. In the previous video about the theory for gradients, we have seen a lot of methods in order to stop tracking gradients midway when we are creating the computation graph. So we have already seen that we can turn on gradient tracking for any variable by using the requires_grad parameter and assigning it a value of true. And next, any kind of operation that we perform on that variable is going to be part of the computation graph, and it's going to be a function, and it's going to be assigned the function, the grad function attribute, and it's going to be given a name. Now let's print out the original x and the function y. Here, this is the original tensor containing 3 elements, and notice that the requires_grad attribute is true. And for the second y, since it is a function and part of the computation graph and it's an addition operation, it's going to be given the name add backward. So what if we perform the same kind of operation, but if we don't want it to be part of the computation graph? So PyTorch provides us with a method known as nograd, torch.nograd, and any code that you provide here is not going to be considered part of the computation graph. This might be useful in certain cases when you're trying to create complicated computation graphs, but if you are performing some operations which are not going to be considered to be part of the original computation graph, you can just use this method to avoid gradient tracking. So if we perform the same operation here and print y again, since this block of code is under the nograd method, notice that it's not being assigned the grad function parameter, and it's not part of the computation graph. So even if you call the .backward method, it's not going to compute any gradients. Calling the backward function will cause the gradients to be accumulated in the grad attribute of x when using multiple iterations. So when you train a neural network model, most of the time you have to use multiple iterations for the training procedure. And if you perform a certain operation and put it inside a loop, so for example, let's say we created one computation graph and we're performing it multiple times for multiple iterations, the gradients which are going to be computed are going to be stored for the first iteration, and then for the next iteration of the computation of the gradients, they're going to be added to the previous gradients. And we need to avoid this problem because the gradients must be computed every time we run the iteration. We need new gradients, and we don't want them to be accumulated into the original gradients. So one thing we can do is remove the original gradients and store the newly calculated gradients for the new iteration. Notice when you are working with neural networks, you might have parameters and you want to update those parameters by using the newly computed gradients. But if you accumulate the gradients, you cannot distinguish between the gradients of different iterations, and updating the weights by using accumulated gradients is not going to converge your model. So here we're going to create a new computational graph, and we're going to assign it to the variable weights. We give it the name weights because it is similar to the parameters that we're using, but here we're using a simple example. We're going to create a a tensor of ones, and it has 4 elements, and we are going to assign a value of true for the requires grad attribute or parameter. After we initialize the weights, then we run this code for 3 iterations. The first thing that we're going to do is multiply weights by 3. Notice that since we have turned on gradient tracking for the weights variable, any operations that we perform on it is going to be part of the computation graph. First, we have a multiplication function. Then we're going to use the reduction operation sum. So this is going to be a tensor of ones, or maybe we can print the weights variable and see the output. We have 4 elements and all of them are ones. Next, we're going to multiply each one of them by 3, and the new output is going to be 3, and we're going to have 4 3s in this tensor. Finally, when we add the sum function, it's going to add all 3s, and then we have a scalar output. Model output is going to be part of the computation graph, and since the last operation is a sum operation, it's going to be assigned the name, maybe related to this reduction operation. Finally, once we get the final output, we can call the backward method to compute the gradients. Notice I've mentioned before, if you don't call the backward method, then the gradients are not going to be computed. Finally, if you want access to the gradients that are calculated after performing backprop, then you can use the .grad attribute of the original variable in which gradient tracking has been turned on in order to see the newly computed gradients. Notice that the gradients are being accumulated on different iterations. The original was all 3s, and we didn't remove them, so it's going to accumulate and add. It's going to multiply weights by 3 again, and it's going to be 3, and then it's going to add them again, and it's going to do it multiple times, and finally we're going to have a tensor of 9s. We don't want gradients to be accumulated when training a neural network. So in order to avoid this problem, well, we have to zero them before performing the next computation. So this is the same thing as before, and the only thing that we add is weights.grad.zero. In a previous video, we have seen about in-place operations. In-place modification occurs when you put an underscore after the function's name. If you don't use the underscore, the zero function just creates zeros. But in the case of an underscore, it's going to modify the weights variable in place, which means it's not going to create another copy, and it's going to replace the original weights. Notice that the original weights were all ones, but once you call weights.grad, you will see the gradients, which is 3 in this case for the first iteration. Then when you call .grad and then .0 with an underscore, it's going to replace the original tensor with zeros, and the newly computed gradients will be gone, and then you do it again. So in-place modification means that you can replace weights with a newly created value, which is 0 in this case. Now you see the difference between the first and the second output. In the first output, the gradients were being accumulated, but for the second output, once the first gradient has been calculated, it's going to be replaced by zeros before the next iteration, and then when it reaches the function again, it's going to compute the gradients and their series again, and then we're going to zero them before the next iteration. And finally, when we do it again, then it's going to be all series again, and then finally we zero them before the next iteration. Here, in the next lesson, we will use optimizer to zero the gradients. This is just one method in which you can avoid accumulation of gradients by using in-place operation of the grad attribute. But after we learn about optimizers in the next video, we're going to use an optimizer to zero the gradients, because optimizer has its own method known as ZeroGrad, which does the same kind of operation, which is replacing the originally computed gradients by zeros before the next iteration. Next, we're going to talk about backpropagation. So let's assume that we have a simple forward pass here. We have an input x, and when we perform an operation a on x, we have a of x, and the output from this will be y. And then when we perform another operation by, the output will be z. So when we move forward, dy by dx and dz by dy will be tracked by PyTorch. Once we call the backward function, then the backpropagation begins. In order to compute dz with dx, which is the final computed gradient, we're going to have to use the intermediate gradients and multiply them by using the chain rule in order to get the dz with dx. So to get back from z to x, first we have to go from dz to dy. Then we have to go from dy to dx, then multiply them together to get the final dz with dx. Now let's see this with an example. Here notice that we have a multiplication function, and we have two inputs, x and y. And finally we have z as an output, and this z is going to go to the loss. So if you want to go back and compute the loss with respect to x and y, which are the gradients, you need to consider the local gradients, which are the intermediate gradients, in order to compute the final gradient by using the chain rule. So in this case, to move backward from d loss to dx, first you have to compute d loss with dz. You have to go from loss to z. Then you have to go from dz to dx and multiply them together to get the final output. Notice in this case, when we are computing the gradients, the local gradients, dz with dx, z is x times y. So here, when we take the partial derivative of xy with respect to x, you can consider y as a constant, and it's going to be y. If you are going back to y and gradient tracking has been enabled for y, then you have to take the derivative of z with respect to y, and the partial derivative of xy with respect to y will be x. So remember that whenever we are creating a computational graph using PyTorch, the first thing that it's doing is computing the loss, forward pass. Second, we need to compute the local gradients because they are important for computing the final gradient. Then, by using the backward pass, we can compute the d loss with d weights, which is the final gradient, using the chain rule, by multiplying the local gradients together using the chain rule. Now we're going to see another example, but this is going to be slightly similar to linear regression. and we're going to see how it works by using a simple function. Notice here that we are replacing the y with a w so that they're similar to the weights of a model, or the parameters, and x are the inputs. Here we're using a simple multiplication function, and y hat is going to be the output from our model, which is the weights multiplied by the inputs x. For the forward pass, if you want to compute the loss for a linear regression algorithm, the most simple, or the simplest kind of loss is known as the mean squared error, and it's computed by taking the difference between the prediction from your model and subtracting it from the target or label y. Notice that we are passing another variable y, which is going to be the target or the labels for your inputs. For example, let's say the input is from the MNIST dataset and you have an image of 0. The label will be a 0 for the image x, and when you perform mean squared error, then you have to take the difference between y hat and y and then square them. We have one final function because squaring is also another computation before getting the loss. This is just the forward pass. Then we have finished following the first step, computing the loss. The second step is computing the local gradients. In order to do that, we have to, the target is to compute d loss with respect to dw. Notice that we are not computing gradients with respect to x, and we do not enable gradient tracking for this tensor, but we enable gradient tracking for the weights, and we need to compute d loss with dw. To get d loss with dw by using backward pass, we need to get the intermediate local gradients, d loss with ds first. We have to get back from loss to s, then from s to y hat, and then y hat to dw. Here in this case, d loss to ds, and from d loss to dy hat. In order to get from d loss to dy hat, you have to take the product of d loss with ds and ds with dy hat first. And once you compute d loss with dy hat, then you can go back to from d loss to dw by multiplying the d loss with dy hat with dy hat with dw. So this is basically multiplying d loss with ds, then ds with dy hat, and then finally dy hat with dw. Now let's see this in detail and use some numbers to make the calculation easier. So the first thing that we need to calculate is d loss with ds, and here you can see that d loss with ds can be computed by taking the partial derivative of the squared error with respect to s, and since it's a square, then this partial derivative will be 2s. When we compute ds with respect to dy hat, then notice that s is y hat minus y, because it's the difference between y hat and y. Then when we take the partial derivative with respect to y hat, it's only 1, because since we are taking the derivative with respect to y hat, y is considered to be a constant, and the derivative of a constant will be 0. You can get rid of it, and the derivative of y hat with respect to y hat is just 1. and we move backward, and when we compute the final local gradient dy hat with dw, notice that y hat is w times x, and we can replace y hat by wx, and when we take the partial derivative with respect to w, then you can consider x as a constant, and it will be x, because the partial derivative of w with respect to w is 1. Then finally, when we substitute values to see what's happening here, notice here that in order to compute d loss with dy hat, which is the intermediate one, it's going to be the product of d loss with ds multiplied by ds with dy hat. Since we have already computed from the previous slide for d loss with ds, we can just substitute 2s here, and then ds with dy hat is already computed, and we have 1. And finally, when we substitute the values 1 and 1 here, w times x will be 1, and y hat will be 1. Then here, when we subtract, let's say 2 from 1, then 1 minus 2 will be minus 1, and s will be minus 1. And finally, when we take the square of minus 1, we get a 1. We're substituting values so that we can simplify the computation. So here, since when we calculate s, we got minus 1, we can substitute s by minus 1, and the final output will be minus 2. Now we have finished computing d loss with dy hat. Our target is d loss with dw, so we have already computed d loss with ds from here to here, and we have already computed d loss with dy hat from here to here, which was the product of this one and this one. Once we get this one, the final step is to get from here to here. So in order to get from here to here, we have already computed d loss with dy hat, and we're going to multiply it with the final dy hat with dw. Then d loss with dy hat will be minus 2, because we have already computed here, and dy hat with dw is x, and since x is given as 1, when we replace x by 1, it's going to be minus 2. So after all of this computation, the forward pass and the backward pass, the final gradient that we're getting from PyTorch must be minus 2. So whenever you want to calculate the d loss with respect to the original variable, it's going to be the multiplication of the local gradients. Now let's see this using PyTorch. First, we're going to import torch, and we're going to create a tensor and pass 1 as an argument, since we have assigned a value of 1 to x. And since we're not tracking gradients for the variable x, notice here we're not passing the requires grad parameter. For y, it's going to be our target variable, which is going to be the label for our model, and we're going to give it a value of 2, just like in the diagram. And for the weight, since we are tracking gradients for the weights and computing the local gradients with respect to w, we have to turn on gradient tracking by passing the parameter requires grad equal to true. The first thing that we have to do is do the forward pass and compute the loss, and after we finish computing the loss, then we can perform the backward pass by using the backward function. So in order to do the forward pass, first we need to multiply w by x, which is going to be the first step to compute y hat, and y hat is going to be part of our computation graph. Second, we're going to take the difference between y hat and y, which is going to be the second step. And finally, we're going to perform the square operation on the difference between y hat and y and assign it to the variable loss. And loss is going to be our final output. Notice here that the loss is going to be 1. So our calculation was correct, and it's going to be assigned a grad function because the final output is a square function, and it's going to be assigned the name pow backward. The next step is to start the backward prop process, and when we do the backward pass, we're going to compute the gradients, these local gradients, and finally it's going to multiply these local gradients to give us the final gradient, which is going to be accessed by using the .grad attribute. So we're going to call the backward method on the final output loss, which starts the process of computing the gradients, and the grad attribute gives us access to those gradients. Notice here, according to our calculation, that the final gradient is -2, and this is similar to the output -2 here. That's all for this video, and in the next video we're gonna start to discuss about the optimization algorithm known as stochastic gradient descent, and the concepts that we have seen so far are going to be very essential for the concepts that we're going to add in the next couple of videos. So we're going to build on top of the concepts that we have learned before. Thank you for watching this video, and subscribe to my channel.
Audio Jungle.